So I did my presentation on basically differential equations. I'm going to do a quick method on how to find or how to solve for a differential equation, and then show some graphs of applications. But first I wanted to touch on what I guess a differential equation really is, and that would be an equation that kind of relates a derivative of a function to the function. So an application, you could say that a function represents like a quantity or a state, and the derivative would be that rate of change for that function. To kind of go over, this is just a really general example, pretty simple, of a basic, it's called a separable equation. And I'm not going to go step by step on how, I mean, you can kind of see what's going on. It's a homogeneous equation actually because it's equal to 0. But we're subtracting over our p function and then separating, putting our x's with our dx's, y's with our dy's. And then we're integrating. And what you get is, I mean, the most important thing really is that constant c at the end. So your final differential equation, that bottom one there, you're solving for y, essentially. And that would be this one right here. I mean, it's just a very general solution to a basic separable equation. I just kind of wanted to show you the gist of how to find a differential equation from such a function. In terms of applications, though, differential equations are very applicable to all sorts of disciplines. I mean, physics, biology, chemistry, even economics and business. This one in particular is called the prey-predator model, where x would be your prey, y would be your predator. And you can see all those other variables up there, those little things, those are just parameters of interaction between your two species. So I'm not going to go into really exactly what they mean, but you can kind of see by the graph here, and in this case a rabbit and a fox. Rabbit's that blue line, fox is the green. Kind of see as the rabbit population goes up, which would be the prey, the fox population tends to go up just a slightly later than the peak of that prey population. Well, obviously when that happens, the prey population is going to go down, when the predator population rises, which ultimately leads to that predator population eventually falling, which leads to the prey population rising. I mean, it's an endless cycle, hence the prey-predator cycle. Very commonly used determining this relationship between different animal species in nature.
Yep. Can you go back to that for a moment?
Yeah.
So, is there ever a case where the two populations sort of approach an equilibrium, and it's like this is the exact amount of rabbits for this exact amount of foxes, and then they just sort of stay steady? Or does it really sort of does it damp, or does it always stay sort of the same?
It oscillates usually. I mean, it doesn't really plateau, I guess, if that's what you mean.
Or damp out to a steady state solution or anything?
Right. I mean, it would. I mean, those are determining factors too. I would suppose maybe if there was a sudden onset of a certain disease or something, it could do that. But just in general, in a general case, in maybe a confined environment where nothing like that would happen, this is what you would get almost all the time. Chemistry example, this is a very general form of a second order chemical reaction, where A would be your concentration in moles, K is just a constant rate, and with relation to time. So you can see in this case we have H2O2, that reaction is tending downward. I mean, obviously you're going to have an instant reaction, it's going to kind of flatten out towards the end once the reaction calms down a bit. So this is, again, just a very general example of a second order chemical reaction that includes differential equations. Economics model, this is very common in macroeconomics, used by big businesses, corporations, called the Solo model. Again, a differential equation with capital, your K, related to time, also involving shares and depreciation. But basically I just wanted to show that you can model, and actually this larger, or the upper blue line here, is the differential equation for that, which involves total output is what you're trying to find for a function of capital, human resource, or labor, and A would be your knowledge or technology, and how that changes with relation to depreciation, investments, that sort of thing. Just another application of a differential. And lastly, I wanted to look at sort of I guess it's a physics model. This is Schrodinger's equations, time dependent and time independent, for the change of a quantum state. And it's just interesting. I mean, Schrodinger himself was a genius, but he pretty much derived these equations just out of nowhere. I mean, I don't know if you know who Richard Feynman is, a brilliant physicist. He was just in awe by what Schrodinger did. But again, differential equation, that kind of hard to see. But they model with quantum mechanics, wave-particle duality, stuff like that, just basic physics. But I just wanted to show you all the applications that come from these differential equations. Get a better understanding of how they're used.